usual way. Today I'm going to talk about one of the projects that we do at JetBrains Research, and as I think you all figured it out, it will be about Kotlin and Kotlin code anomalies. Well, I'm not here to officially promote Kotlin. We have specially trained people for this, but we have to understand what we're looking at. So another show of hands, how many of you tried Kotlin? Whoa, this is awesome. Anyway, so brief introduction. Kotlin is a general-purpose statically typed programming language that both features object-oriented and functional features. So it was designed to interoperate with Java fully, and originally it was targeted at JVM and Android platforms, but now it can be compiled to JavaScript and even to native code via LLVM. It's open source. It's relatively young, but have active and continuously growing community. So we should focus on the tooling around this language. For most people, Kotlin looks like a more streamlined version of Java, with its extension functions, coroutines, properties, nullability analysis, and different features. And when people use these cool features, their code generally becomes more clean and concise. But there are always people who do things differently. For some reason, we have an implementation of fourth compiler in Kotlin. You know, this stack-based language from the 70s. Who knows why it was written, but as GitHub states, it's written in Kotlin, 100%, and sometimes it doesn't look like Kotlin at all. We call these code fragments anomalies in a way that they're good code. It's syntactically correct. It may even work very well, but it doesn't look like the code that other people write in this language. And these code fragments are actually of great interest to language developers because, well, they could show some previously unnoticed compiler bugs or highlight some compiler performance issues, or even could be used to get hints on how to improve the language further. So the informal tag description that we've got from the Kotlin developer team was take all Kotlin code in the world and bring us some weirdly looking programs. And like in risk management, it's pretty hard to plan for known unknown, and it's much harder to plan for unknown when you don't know what you're looking for. Before we clarify what this could mean and how to achieve this, let's see what can be done in this field. If you Google code anomaly detection, you find something. Some of the papers listed here, the first two of them are based on static analysis. The first one presents GrooveMiner tool, which tries to detect anomalous objects interactions. So it takes the code, builds a directed acyclic graph that features constructor method calls and their dependencies, and tries to apply graph anomaly detection techniques to find atypical areas in this graph. The second one uses somewhat similar idea, but they build usage models of objects using their sequences of method calls. And they also apply graph-based anomaly detection techniques. They are very helpful if you're trying to find bugs in your programs. So these approaches basically target language users, not language developers, as we are intended. The next papers are based on dynamic analysis. The deduce tool tries to run your program and store every value of every expression that it encounters. And it tries to induce some invariant rules. And when these rules are violated, for example, some expression gets a value that, well, it differs a lot from all its previous values, well, it's considered a candidate anomaly. The last one here also runs the program, but collects traces of system calls, but nevertheless, we have a huge data set in mind. And, well, projects have all kinds of weird dependencies, and who knows how they're supposed to be run. So I think we should limit ourselves with static analysis only. Okay, getting back to the task at hand, what should we analyze? Originally, we targeted the regular Kotlin that works on the JVM. So we have the source code and the bytecode produced from it. We should analyze both of them because analyzing source code gives us patterns in incorrect language use, while analyzing bytecode provides us with compiler issues. But what's best, we can combine these analyses together. For example, we could search for code fragments that were not anomalous in the source code representation, but became anomalous in bytecode representation. And that's clearly an issue of some kind. Next, at what level should we look at the code? Well, obviously, looking at operators, single operators, or lines of code doesn't make any sense because they don't capture structures complex enough to form an anomaly. Functions seem like a good choice because they're large enough to have some code that can form an anomaly, but small enough to represent one single operation on a class. Classes also seem like a good choice if you want to look for anomalies in inheritance, in function signatures, or control flow, for example, to long chains of function calls whatsoever. Files could be used if you want to search for anomalies in class interaction, and projects seem too large and too domain specific. You can't actually analyze the project without knowing what it was created for. So, moving on to how. There's data science and there's anomaly detection techniques. We could use a standard task of anomaly detection on vectorized data. And then when we get some anomalies, we should somehow classify them according to the type. And that's another task. Another challenging task. Speaking about code representation, it's really a hot research topic right now. But basically, all these approaches fall into two categories. The first one are explicit features, basically software metrics like the height of the AST or cohesion coupling metrics. And some natural language processing features like bag of words or their derivatives. These features are very descriptive. So you just look at the vector value that you've got, and almost always you have a good hypothesis on what's wrong with this code and why it was considered an anomaly, which is very good. But these features are hard to choose. Because, well, first of all, software metrics are very, gray area because they mostly rely on opinions on what good code is, and this is highly subjective. Also, it's hard to choose them because when you don't know what you're looking for, so you have to precisely specify what are you looking for with these metrics. There's also path-based representations, trending approach that basically allows you to traverse the tree and collect all the nodes types in this syntax tree that you encounter, and then use these paths to do some research on it. An alternative here is implicit features that mostly could be described as n-grams, some kind of neural networks processing, AST, hashing, and different kinds of distributed representations. While they're very, they obviously lack expressiveness. You get some vector of numbers and you can't understand what this really means. But they can capture some properties that were not obvious beforehand, so they could be very useful too. Speaking about classic anomaly detection task, you can do a lot actually when you know things about your data. Our data is all Kotlin code in the world, and you can hardly make any assumptions about it. You don't know your distribution type, well, nothing. So we have to be really careful here when applying these techniques. The first two here, just a brief overview. The first two here are very popular outlier detection techniques. They are good because they're assigning an anomaly score to each of classifying objects and not just perform a binary classification. Also, they do not make any assumptions about distribution of the data, which is good in our case. Some clustering algorithms, including listed here, well, also could be used for anomaly detection, since they don't prefer that each element should be put in in some cluster. Autoencoder neural networks is really fun tool because basically it's a neural network that has input and output, that has the same data as input and output. And using its hidden layers, it tries to learn the identity function, basically. So the first part of the autoencoder is a decoder, which tries to reduce the dimensionality of your data and, well, create a hidden layer of values. And the second part is encoder that tries to reconstruct your data from these hidden reduced dimensions. And if you get a reconstruction error, if you observe a reconstruction error, meaning that your predicted value differs a lot from your actual value, that's an anomaly candidate, and you can just do it like that. There's also one technique here which is not unsupervised learning technique. It's a semi-supervised learning, meaning that you have to get some labeled data to train the classifier. But it also used for outlier detection, and well, basically if we get some results, we can pass them to this one class SVM and get more results. So there's a number of algorithms available to solve our task. So let's talk about what we have done so far. The workflow here is pretty straightforward. We get code from GitHub via GitHub API. We cloned and changed the compiler a bit to serialize all syntax trees that it builds. We ran feature calculation on these trees. We ran algorithms on these features. We look at the result and repeat. At some point, we take all anomalies that we've got, go to Kotlin developer team, show them, and see if we need to change a course. Today, I'll talk about 3 experiments that we've performed last year. Well, now the data is different. For example, for last year, the amount of Kotlin code has doubled on GitHub also. But anyway, we fetched all repositories that stated Kotlin as their main programming language, that were not forks of any repositories, and that were created before March. And that left us with, removed the duplicates, and that left us with about 4 million functions and, well, 9,030,000 lines of code, source files. We decided, in these initial experiments, we decided to stick with functions as our analysis level. Well, that was a design choice. So the first experiment was very straightforward. We used explicit features and collected 51 of them, describing different aspects of the code, as you can see here. So we get, for each of 4 million functions, we get a vector of 51 numbers, which we managed to reduce to 20 using the PCA. It's a reduction, dimension reduction algorithm, which led us with pretty much the most of the variance that we needed, but much more friendlier computation time. We ran local outlier factor and isolation forests on it. The contamination parameter here is basically the proportions of outliers in the data set. And this is another design decision because we have no idea how many anomalies is there. So we just set it to some small number, like 0.01% to keep the results observable by humans. That led us with 0.01% of 4,400,000 functions, which we manually observed and selected 322 anomalies that could have been of interest to language developers. Another experiments used implicit features. We used n-grams, namely uni, bi, and trigrams, on the syntax tree. This simple image shows the bigrams and trigrams on the syntax tree, but the idea is quite similar to these path-based representations, but simpler. And we use autoencoded neural net to detect outliers here. We experiment. It was very simple architecture with only one hidden layer. We experimented with the compression rate of the hidden layer and got around 360 anomalies. So we brought these anomalies together and removed the duplicates and still got a lot of anomalies that we were not sure were useful or not. We looked them through and manually labeled them. We got 23 types. We created a simple web interface that allowed Kotlin team developers to rank these anomalies one by one from 1 to 5. And 12 out of 23 types were considered very useful, meaning rank 4 and 5. This table shows this E1 column is experiment 1, E2 is experiment 2, errors rank. As you can see here, most of the anomalies that were considered useful were lots of something. It's not that fancy and weird as we anticipated to see, but developers still found these anomalies useful and used them in their tests. Some examples. This is an anomaly this is a function with a when statement having about 120 case branches. I sincerely hope it was automatically generated. This one is a function with 22 generic type parameters. Actually, this one is very useful because our recent finding was that compiler does a lot of work around generics. And in some real complex cases, it could even reach exponential complexity inferring types. So code examples like this are actually very useful for tests. Well, this is some weird test function. Actually, this fourth compiler that I have showed before actually also have fallen to this strange code constructs group. And this one is good. This allowed us to file a bug to a parser. This obviously incorrect 400 plus lines of code actually break the parser with the Stack Overflow error. So we filed a bug. And the third experiment here that I'm going to talk about is features both static source code analysis and bytecode analysis. Still, we don't want to compile any code ourselves, but we need bytecode. What do? We created a tool that crawled GitHub and tried to find released jar files for projects. It downloaded the files, grabbed metadata from it, and tries to search source codes for these packages. That way, we managed to grab around 40,000 source files and bytecode for them, so we can compare the anomalies. The approach was the same, using n-grams and autoencoder network, and we looked for anomalies in one case and not anomalies in another. That led us with 38 conditional anomalies, which one example that I will show you is this 10 lines of code function that turns into 4,500 bytecode instructions. Well, this is not actually a bug in a compiler, as it turns out. It's a bug in the framework, or not a bug, but, well, design feature. Someone wrote a very complex bind function that was inlined, and someone wrote a code that inlined it 9 times in a row, so it resulted in a huge bytecode. And that's an interesting example because looking at the source code by itself, you can never guess that that's some kind of a weird code. So these were our initial experiments. Now we are trying different algorithms for anomaly detection, different code representations. Now we have some labeled data, and we are finally free to use semi-supervised learning, like active learning or some other fancy stuff. A lot of our pipeline is still made by hand, for example, clustering and labeling of these obtained anomalies, which should definitely be automated. We can look at different structural levels, not functions, but classes. On the other hand, we can look at feature-specific anomalies. For example, look for anomalies in loops, or look for anomalies in function signatures, and so on. We could look for anomalies in object interactions and some other ideas that were presented in the papers that I mentioned before. We can go deeper in the compiler and see which optimizations produce anomalies of any kind, and so on. And there's always Kotlin for Android, Kotlin native, and Kotlin JS, each of which is a completely different world with different anomalies. So, to sum up, even our first very straightforward experiments showed some useful results. Our work is open sourced on GitHub. Also, here's our research group page. If you in some way interested in our work, feel free to drop us a message. And thank you very much for listening.
We have some time for questions, so if you want to just raise your hand.
Yeah.
So you mentioned that you used an autoencoder to find anomalies. Did you relate other types of algorithms?
We have here. The question was about whether we tried some other algorithms to instead of autoencoders. Well, for implicit features, we haven't. Well, basically, we tried to see. Well, we have a lot of stuff to try, and we wanted to see if any of it works. Because when we got the task description, just find us anomalies, we weren't sure if we succeed at all. So we just tried this and this and this and this and got something working. Yes, now we are doing different, more scientific approach when we try different algorithms on the same data and compare and stuff. But I'm not sure I can talk about it yet. Other questions?
I'm curious, are there already some cases which found anomalies have influenced language design besides bug fixes in parser?
Yeah, the question is whether anything that we found so far influenced the language design decisions. I'm not sure. That's the short answer. The more detailed answer is that you don't really. I think you can't really see that obvious. What makes people who take decisions do this. So we have presented several anomalies that could have led to some decisions, but I'm not sure if they will be taken into account. But already we had some feedback, some positive feedback on some anomalies that were, they could be used. I hope they will be used, but I think that takes time and some process. It doesn't work like that. Thank you.
Any more questions? Okay, so thank you very much.
Thank you.